Okay, thanks for inviting me. My name is David Forde. I work for EcoH Technologies, and my background is automation, robotic development and new technology design. I got introduced to our CEO, Vince, of EcoH Technologies, and we very quickly developed new concepts and ideas for energy storage. The idea of this presentation is to give you an understanding of what energy is, what energy storage is, what the difference between the terminologies are. So you've got power and energy, and how you can utilise this to resolve some of the issues that you have at the moment in the mining industry. So you have power in mines, you have power everywhere, but it's not just getting power from A to B or from utility to the source or from generators to the source. You need quality of power, you need reliability of power, you need continuity of power. And these are some of the things we're going to be talking about briefly. And then we're going to come on to safety, obviously the environmental benefits with energy storage. We've all heard the green terms, so I'll go over those very briefly. And then two specific examples in the mining industry for hybridization, one for above ground mining and one for underground mining. So before we go into too much detail on energy storage, I just want to clear up a few terms. I know a lot of people here are high level management and senior. I don't know how many people are that technical. And a lot of people think that energy and power is one and the same thing, like voltage, frequency, current, kilowatts. A lot of people, it doesn't make any sense. Some people, it just clicks. So I'm just going to briefly go over some of the terms you'll hear in the energy storage market for batteries, state of charge, etc. So power. Power is kilowatts. It's measured in kilowatts. So these lights are 100 watts. Okay, so power is the size of the power that you've got. Energy is the duration you can sustain that power. So for example, if you have a battery that's 1 megawatt and 1 megawatt hour, you can draw out of that or discharge that battery at 1 megawatt for 1 hour. It's a very simple linear relationship as well. So somebody here mentioned numbers, but she's just left. That's great. So you've got 1 megawatt for 1 hour. That's a 1 megawatt hour system. But if you draw 500 kilowatts, you can then draw that for 2 hours. 250 kilowatts, you can do it for 4 hours, and so on and so forth. So it's a very simple linear relationship between power and energy. SOC, state of charge, how much power is in the battery is measured in percentage. So if you have a typical 9-volt battery, that'll be fully charged, that's 100%. When you take out 50% of it, you've taken out 50%, so you're left with 50% depth of discharge. The way I remember this, there's a small d at the end of discharged, so it's what's discharged. So if a battery or an energy storage system has a state of charge of 40%, then it's discharged 60%. So there's a relationship. EOL, you'll hear BOL and EOL. BOL is beginning of life, EOL is end of life. The beginning of life is obviously a brand new system. EOL doesn't necessarily mean that the system has to be thrown away or discarded at the end of life. If it's got a 5-year warranty or 10-year warranty or extended warranty, EOL basically means that you only have 70% of the available capacity to recharge. So if you have a 1 megawatt hour energy battery system or energy storage system, the end of life means you can only now store it back up to 70% of its original capacity. So that 1 megawatt hour system is now only 700 kilowatt hours. C rates. These are what battery companies play with, and they tell you the truth when it benefits them, and they just do a lot of marketing gumph as well. And I'll explain this in a bit more detail. So if you have a battery system or energy storage device and it's got 1 megawatt hour, so you discharge 1 megawatt for 1 hour. If it's got 1C recharge rate, then you can throw 1 megawatt back into it, and in 1 hour it's recharged. Again, very simple math. If it's got a 2C charge rate, then you can discharge by 1 megawatt. You can throw 2C or twice that power back into it, so you can recharge in half the time. Lithium-ion technology is now getting close to 5C for discharging and for charging, depending on the battery chemistry that you use. Lithium-ion, phosphate, manganese, etc. We use nickel cobalt, and we use LG batteries and SAFT batteries, and we've got up to 2 and 2.5 C rates now. So they're improving all the time. But what some energy storage manufacturers will do is, instead of having one battery and doing a test on one battery, they'll put 10 in a line or 20 in a line or 100 in a line and take the average. And that average generally is higher than it is for one individual battery. So you get sort of inflated numbers. So you need to be aware of what you're actually getting. I'll put this on here to show what typical lithium-ion batteries, what the depth of discharge is and the number of cycles and what it all means. Because it's all about this big word here, cycles. Cycles is the key in lithium-ion technology. When you buy a battery, you don't get a warranty for 1 year or a guarantee for 1 year or 2 years or 3 years. You get a number of cycles, and this is a logarithmic. Numbers ladies back. So this is a logarithmic curve. So you're basically adding a zero each time. So for example, a typical handset cell phone, BlackBerry or Android, will have 300 cycles, or be designed to last approximately 300 cycles. So that's 100% state of charge, down to zero, back up to 100% state of charge again. One full cycle. 300 of those, and the battery is deemed end of life. We've just seen that end of life doesn't mean dead, it means you can only recharge back up to 70%. Now the chances of people discharging from 100% to zero and back up every day is zero. Everyone has a phone charger on the phone, in the office or in the car or at home. So that 300 cycles, if you only discharge to 50% and back up to full again, you've only used half the cycle. So now logarithmically, you've now gone from 300 cycles to 3,000 cycles. If you discharge at 25%, that 3,000 cycles is now 30,000 cycles. Consequently, if you discharge to 12.5% and back up again, you've now got 300,000 cycles. So you can see how you use the energy storage and how you use the energy, not the power component, the energy, will dictate how many cycles you have, and that will dictate the life cycle of the system itself. We dragged the oil and gas industry kicking and screaming into the 21st century with energy storage. We were always told that you're never going to get into oil and gas because everybody wants big black smoke. Oil rigs on land and gas rigs on land, they're designed for peak power. So when someone's designing a rig, they'll work out that at one point in time, if everything's switched on, and the worst case scenario, you'll need 4 megawatts of power, there'll be 4 1 megawatt generators there, and they'll all be on. They're all needed. The average power might be 800 kilowatts, but you still design it for 4 megawatts. That's the philosophy, that's the mindset. So with our energy storage system, we could go to an oil and gas industry, take up all these transients, these megawatt plus transients in both positive and negative. So now we're charging and discharging at the same time. And we noticed that we could switch off not 1 generator, but 2 generators. So now you have 4 generators, one's a backup, 3 are running. 2 of these were switched off, leaving 1 generator on running itself for up to 20 to 30 days with a battery storage system, taking up all the transients. So what we do is an energy storage system, as you know, it charges and discharges. So it's a load and it's also a generator. And it switches between the two very, very quickly. Typically sub 1 cycle or sub half a cycle if you're looking at a sine wave. So the switching is very, very fast between charge and discharge. And because of that, we can pick up transients and we can counteract them and allow for these high loads and drops in frequency and drops in voltage as well. So we know this in commercial, we know the industrial, military have been using renewable energy for a long time. We've actually developed a system for the military, which is a portable containerized solution, which just drops in right at the very front line for communication and for power for the guys who are in the field. And then there's a zero heat signature and there's zero noise. Once it's depleted, it picks up again, drop it off, put a new one down. And it gives immediate stored energy to the front line for the armed forces. Obvious solutions, again, these are the sort of terms that we're all aware of. It's all green industry. We read about companies doing this thing all the time. A few we might not be aware of down here, global adjustment and peak demand management. That's pretty much just for Ontario. But I will go over those because they're quite important, and I was specifically asked to mention this towards the end of the presentation. Again, there's a lot more numbers involved in this, so a few people will be happy with that. Quality of power. We said, yes, you get power from the utility or from generators to where it needs to be in the mining or in your production process. And typically that's what you should be getting. Perfect amplitude, positive and negative. Nice and simple. Very sinusoidal. If there's a blip in frequency, which could be something to do with the engine, it could be dirt in the fuel, it could be ice on the line, it could be utility, it could be anything. We don't know what it is. But occasionally you get blips in frequency. And that causes issues with VFDs and computer controls and automation systems. Because what they tend to do is they shut themselves down to save themselves. So a typical VFD control system runs on 60 hertz supply, or motor control, or any computerized system, and it has a tolerance of, let's say, 5%. So if that frequency goes to 65%, it'll still operate. If it goes to down to 55%, it will still operate. If it goes out of that range, then it causes big problems for the actual hardware itself, and the software finds a problem with it. So it kills itself and it shuts down. So there's no way to determine or to predict when these are going to happen, but the result is that things shut down, hardware shuts down, again, to save itself. Similarly with voltage spikes, we can see a huge voltage spike here. A little bit of math, just very quickly, because I won't bore you. Watts is proportional, or watts are proportional to voltage and current. So you can have a high voltage, low current, and have the same watts. You can have low voltage, high current, and the same watts. So you get the same output here, but because you get a spike in the voltage, then that means your current could drop. Consequently, you could get a drop in the voltage, which means the current's going to spike. So again, that causes issues for hardware systems and VFDs and controls. Reliability. So now we talked about quality. We talked about continuity. Now reliability. You need to make sure you get power all the time. So we've got good power now. How do we maintain it? How do we make sure that it always gets to where it needs to be? Energy storage and generators on a typical site. One's out for maintenance, and you've got, depending on the site's load capacity, you could have 3, 4, 5, 6 megawatt generators to feed the standard AC bus. This is just an AC line bus for those of you that aren't electrical. It's just a big copper bar, buzz bar, everything's powered from there. All to the circuit breakers, to the loads, to the machines, to everything else. If one of these drop out for any reason and there's a fault on the system, then immediately you would lose a lot of power on the AC bus. So straight away, a lot of your systems would start to crash. With energy storage, it's immediate. It's already online, it's already connected to the AC bus, so it's already ready to deliver power. One thing I should point out, a lot of people assume that a binary is like a clock, an analog clock. It's on or it's off, that's it. Binary isn't actually on or off. There's 3 states to binary, or 3 states to energy storage. There's on, off, and standby, or idle mode. So with this system, or this type of system, you can be discharging, you can be charging, or you can be ready to charge or discharge. So you're not switched off. If you're switched off and you have to switch on to respond to one of those peaks or troughs in the voltage or frequency, it takes time for any computer or any hardware system to engage and get ready to up to speed and then do what it's meant to be doing. So this has an idle mode capability, which again is part of the binary system. It's 1, 0, and standby. I've also put this chart down here. Am I going too quick, by the way? Sorry, I'm talking a lot. I'm just passionate about this sort of thing, so I'll get carried away. Mark tells me that. So I'll put this down here just as an example of the difference in energy and power and what you can get. What is a battery? Well, if you want to plug in a laptop for an hour, then you need a very small amount of power, but you need it for 1 hour, so you need an amount of energy, but you only need small power. So it's a big ass computer, you don't need 500 kilowatts, but for example, you can have a 500 kilowatt system just for 30 minutes, or you can have a 500 kilowatt system, which we class as a low power system, for 4 hours. And then these are modular systems, so you can just plug and play. And it physically is a plug and play system, just to an AC bus. So a very small amount of power for a long period. So 500 kilowatts for 4 kilowatt hours. Conversely, if you want to just take over transients or for blackouts, blackout protection, if you're on utility and you lose utility and the generators are backing up to kick in, there's about a 15-second, 20-second, 30-second delay before the generators are up to speed. So in that delay period there, you might need 4 megawatts for 25 seconds or a minute. So you need a lot of power, but very, very small energy components. And it's energy that costs money. The big part of any storage system is the energy. And it was 3 or 4 years ago about $1,200 per kilowatt hour of energy density in a lithium-ion battery. There's a lot of battery chemicals out there now. Nickel cobalt is a popular one, and that's got a large energy component. There's manganese, there's sodium-based batteries, there's heat batteries. I've just been reading on one which is a water battery, which I don't believe exists, to be honest with you. And all of these have different energy densities, and the energy is the bit that costs the money. But now it's down to around $400 per kilowatt hour from $1,200 only 3 or 4 years ago. And we're seeing that come down even more now. So LG, who are the biggest manufacturer in the world, they're now bringing that price down again. And it's just the refining process. It's more recycling. There's more lithium out there now in recycled batteries, so that's now being recycled. So mining is taking a little bit of a hit on that, but it's the processing side of lithium as well. We saw earlier, we had the nice amplitudes. We've got positive and negative on a sine wave. That's what we need. That's what we get in our houses. That's 60 hertz supply. That's generic all over North America. This is a brownout, and this is what your control systems are seeing, and this is why they fail. You get a nice amplitude, it's all even, and then all of a sudden something happens. You see, you need a UPS, you need an energy storage. Can we just edit that out after? Yeah. That's perfect timing, actually. So I hope my boss isn't watching this. So with the brownout, you can see the frequency is now dropping, and that's causing problems with the hardware and with the control systems. Not the bottom buttons. Right, okay. Something that's happened, I say recently, over the last 10 or so years, and we're only going back to the 90s. This is cyber threats. My colleague was mentioning about web-based and Chrome systems, where now you can look over the internet. You don't need actual software and downloads all the time. You can just go online. Well, there's an associated threat with that. Years ago, it was just annoyance and amusement and nuisance people, students just playing about, trying to better themselves, challenges to each other. Now it's getting more and more for personal gain. It was for money, and now it's gone to espionage and weaponization. So it's become a more serious threat. So it's now taken very seriously. So and again, this can be to do with energy storage, because this could affect your utility. All your utility is on smart grid systems. It's all web-based browsers. It's all web-based control systems, SCADA systems, which I'm sure you're all aware of SCADA, and BMS, building management systems. They're all the same interface for operators. So they all use web-based systems. So without energy storage, then you could have a concern with your continuity of supply from utility. So again, previously we'd mentioned you have quality of supply, you have continuity, you have reliability. Well, all of that can be jeopardized because of cyber threats and espionage. The evolution, so safety. This is a big thing. About 8 years ago, we heard about the lithium-ion batteries in airplanes, and there was smoke in one of them, and there's a camera there. I must remember that. I've got to be careful what I say now. We've been told by some battery manufacturers we know why that happened, and it's all been open to the public, and it was due to budget cuts. Instead of buying a very well-designed, proper battery, fit for purpose, a much more economical battery was chosen, and that caused the incident, and it was budgetary costs. Thermal runaway. Well, thermal runaway is what happens with lithium-ion. Lithium as a substance reacts quite badly with oxygen and with water. So thermal runaway is just going to get worse and worse and worse, and eventually gases, and because the gas expands inside the battery component itself, inside the cartridge. It could be prismatic, which is the battery cell you have in cell phones, or it could be the cylindrical ones, which are used in industry. Once it pierces and breaks, then it's open to the atmosphere, and that's when you see the flames, and that's when things get quite serious. So how do we prevent thermal runaway? Well, there's a number of systems that take place before you get anywhere near to thermal runaway. Firstly, all of these batteries are in strings, in rack systems, typical 19-inch racks that you get in IT. There's a few IT people here I think I've heard about earlier. So you're used to IT racks. And all of this is in a standard ISO container with solid steel doors, and they're all shut as well. So if anything happens, it's contained inside that particular unit. Inside there's also a fire suppression system, which is either a Novec gas or FM200, and these are breathable gases. These are the sort of systems that you get in call centres and data centres, where there's a high percentage of people there and a lot of computer power there. So if there is a thermal event, as they call it in the battery industry, and someone's inside one of these containers or these storage units, then straight away they can breathe and they can escape. If they're injured, they can still breathe, and the Novec gas that's released, or the agent that's released, will quench the lithium-ion fire. So it prevents thermal runaway. So big steel box, fire suppression system inside, and that's not including all the battery management systems. So again, these are terms you'll hear: battery management, BMS, battery management system, MBMM, master battery manager, BMM, battery manager. Anything to do with B and M, any way you want to put them, that's a battery manager. Each one of these come from different manufacturers, and they all have different ways of preventing fires and preventing thermal runaways and preventing things going wrong. So you've got your standard circuit protection, your thermal fuses and circuit breakers, etc. But inside these are microcomputers or microcontrollers. And what they're measuring is for overvoltage, undervoltage, overcurrent when you discharge, overcurrent when you're recharging. It's checking the cell temperature in every battery, in every string, in every system, which could be thousands of cells in one full system or one full unit. And it's monitoring all these all the time. And what it can do, it can electronically put a single battery to sleep. If it sees any fault or it registers anything that's out of the ordinary or out of characteristic with what the battery should be doing, it immediately puts that battery to sleep. If that doesn't work, then there's the fusing, which kicks in, and takes out the power. Worst case scenario, it starts to begin a thermal event, and then what happens is there's a cap on each cylinder, and as it expands, there's a weak point in that cap, and it physically breaks. So it stops any current flow. So it immediately breaks that circuit in that particular cylinder in a battery, and that's a mechanical device. So it's physically impossible for any current to flow, therefore it stops that fault in that particular circuit. And these are a lot of the internal redundant safety systems.
It's nothing you said.
Oh, okay. I was going to say a joke then, but I won't. Hybridization. So this is merging everything together. You'll notice that there's 4 symbols here, and one's different to the other. So we're generating power, or creating power. We're creating power, we're creating power, we're storing power. You can't store power as power says. You can store power as energy, because like we said, it's a duration thing, it's a time thing. So with the generators, when you don't need power, you can artificially load them to keep them running at the peak point. Any excess energy generated or power generated, you can then store. So you're now building an energy or power reservoir for the future. Same with solar power, that's fantastic during the day, or when it's cloudy, it's not so good, at night it's not so good, but during the day, excess power, again, there's nowhere to store it. With energy storage, you can contain that for later for future use. Same with wind turbines. This is another one of those slides where we see these words all the time with companies. Everybody wants the public image, green. Look how good we are. We're doing good things for our neighbours, for the local community. Health. Yes, you've got less emissions, you've got smaller engines, you've got less engines. So yes, it's going to be a cleaner environment. So that's a good thing. Marketing people love these. The strategies that businesses have for portraying a green image, because they're using less diesel or less oil and gas and more renewable energy systems. Noise reduction, if you've got less generators, it's going to be a quieter system. So again, the neighbours and the birds are going to be happy about that. Reduction in fuel costs and reduction in fuel storage. This one here, fuel storage, that's something that not many people are aware of. In the oil and gas industry especially, it's not just the fuel cost for running extra engines, it's actually transportation of fuel. Because you don't have an oil rig or a gas rig on site downtown Toronto. It's in the middle of nowhere, it's by Timmins, it's way up north. So you've got to get diesel out there first. So you've got this big haulage truck with belching fumes going all the way out there. Then you've got to store it somewhere, so there's a risk associated with storage. And then the truck leaves empty to go back again, belching black smoke, and then back again. So it's the delivery of the fuel as well as storage. And again, all of these are reductions, all to do with OPEX, bringing down the operational expenses on a site. Smart grid, we have these in homes, but we're seeing this coming into industry now in many different ways. I'll come on to this one right at the very end of the presentation, because it's a new development that we've been looking into. But load shedding, so in Ontario especially, we look at global adjustments in a moment, and one thing that happens in Ontario is if there's a bakery that's just about to switch on down the road and it's 3 in the afternoon, they phone the utility company and say, we're switching on all our ovens, so we need extra power in 2 hours' time. The utility company will then phone around local businesses and ask them if they can curtail power, and they will buy back some of their power that they're not using. So you get paid for running down the business. And then that means that there's no or less stress on the utility infrastructure, and there's enough power now for this bakery to do what it needs to do at that particular time of the day. So that's called shedding load or time shedding. And that's what a lot of companies are now looking into. Again, this is just in Ontario. Improved asset utilisation, well, that speaks for itself. If you've got smart grid control systems, then you know what's on, you know what's off, you know, you can monitor remotely, you've got telemetry, so you can see which engines need a change or need to do overhauls or maintenance. You know what your loads are, you know what your expected loads are historically. You can map and project what's going to happen in the near future. So again, you're utilising your assets much better. And if you have energy storage system there as well, you know how much energy you've got stored for what duration, how much power. So again, it helps you to map the near-term future for all the assets that you've got on your fleet. Modular distributed energy storage is next. Something to look forward to. When we went to New Gold up north, they told us that they had a specific problem they wanted us to have a look at, which was anti-idling. So basically, one driver, 2 machines. Gets in his truck, drives down to the open face, gets in his excavator, leaves a truck on because he doesn't want to get cold cab or warm cab, does what he needs to do, leaves the excavator running, goes back to his cab, goes up to the top, comes back down again to the face. It keeps doing that all day. So typically 14 hours a day. These are the numbers that we've been told. We're anti-idling, so just ticking over. And these are big engines. So with energy storage, you get a much smaller device, just on top of the cabs, and this is what we developed together with a few other companies. So now, they switch off the engines, and all you need is power for heater, lights, C and B scene, and radios. So you need a small amount of power, but for a longer duration. So now you need an energy component, but only a small amount of power. And that saved them, they estimated, more than $200,000 per year. So immediately the ROI is very, very good there and easy to calculate as well. Regenerative braking, this could be to do with mine shafts, it could be to do with a number of different aspects of electrical engineering. But basically, you put electricity into a motor and it spins round. If you take the electricity off and put a voltmeter on that motor and spin it by hand backwards, it becomes a generator. It's very simple electrical engineering. People say it's complicated, it really isn't. So you can see power goes in, motor spins round. You spin it by hand backwards, power goes out the other way. Well, if that power is connected to your utility or your generator, then power is going to go back in there and cause some problems. So regenerative braking is now diverted to load banks or heaters. So now you're burning off all this excess energy. So why can't you use it? Well, you can't use it because you can't throw it back in, there's nowhere to store it. So if with an energy storage system or a battery system, any of this regenerative energy can be used, and again, it all tops up your energy reservoir for later, whenever you need it. This is a concept we were asked to look into, which is, as a mine progresses with its production, different levels, different veins, etc., you have energy storage devices. And these can be either roll skid, there can be trailer-wise solutions, or there can be forklift pocket solutions. And the idea is that we work together with some electric vehicle companies who I believe they're giving a presentation later on this year. And all we're doing is showing that with energy storage, you can add down to the different levels and give you as much capacity as you need, when you need it, and more importantly, where you need it. Depending on the length of the run for the distribution, you could lose a lot of the frequency. There could be sagging down the bottom here. So your 14.8 volts or your 380 volts or 600 volts that comes down, it could be down by 5 to 10%, which again could cause problems for some of the electrical equipment. So by having these systems dotted around, and they just increase as you increase your production with the mines. And then the beauty of it is, you don't need it up here anymore because you've finished that level, you've finished all the ore from there, all the extraction, move it down to the bottom one there. Any questions so far? It's been very quiet. See, I told you, electrical engineering, it's easy. There's no questions. Brilliant. So this is the last one I was asked to have a quick talk about, which is global adjustment. And again, it's just in Ontario. Our CEO has actually spoke to Catherine Wynne and asked her why it's called global adjustment when it's just in Ontario. And she just smiled. And that's the true story. So what happens is, over the summer months, typically that's when more power, again, not energy now, just power is used. There's a threshold now, 1 megawatt. So any industry that uses more than one megawatt, they're now tested every year. So the government or the local utility company will give 5 points of measurement every year. And they'll say, we're going to measure August the 5th at 6 o'clock, September the 7th at 2 in the afternoon. They don't tell you when it is. You have to guess when it is. There are companies out there that predict when this global adjustment event is going to take place. And they're very good. We work with Rodan Energy, and they're very good at this prediction. So what happens is, if you're over 1 megawatt, when they test, when they say we're checking now, then you get an immediate fine. It's a tax. And it's between 80 and 100 and something thousand dollars. And they do this 5 times a year. So now you're looking at $500,000 a year. So if your production is just over $1 million, sorry, 1 megawatt, and they check it, and 5 times a year it's inspected, and it's over 1 megawatt, then straight away you've got a fine or a bill of another $500,000. So of course, with energy storage, you now baseload the utility down to 900 kilowatts. So you've got $1 million worth of batteries down here, and for those events when you need it, you switch on, your utility is down to below 1 megawatt. So when they do the tests and they're looking for those peaks above 1 megawatt, you're now below, so you don't get any fines. So you've got a choice, pay the fines or get energy storage. And it's as simple as that. And we've done a lot of work with big companies who are getting big problems like this. And this is per megawatt. So you've got a 3 megawatt system and you're 2.1 megawatts, you're now looking at double your bills. So it's a really serious problem. It used to be 3 megawatts and it's now come down to 1 megawatt, and that was January the 1st this year. So that's basically global adjustment. Very serious issue. And we get, like I say, we're getting a lot of calls and a lot of people asking about this.